Okay, again, my name is Alan Ambler, and I am part-time working with the Alliance for PE Pipe to bring a civil engineer's perspective to all things that are polyethylene pipe. A lot of the volunteers that work for Alliance for PE Pipe or chemical and mechanical engineers that bring that focus, and a lot of the audience that we're paying attention to here, you guys work directly for the municipality. I wouldn't wish that on anybody. I worked for a municipality for almost 10 years myself, but you happen to be in the place where you'd have the greatest impact on your residents and customers and the like. So I always love to see you attend these events and then embark on your own pipe bursting programs themselves. Matt and I are going to share off informally about it. I will continue to monitor questions as we go through, and I hope you get a lot of good information from this. So here we go. This essentially now we're looking at understanding the basics of pipe bursting. There are multiple mechanisms from a technology standpoint, pneumatic and static, that we'll discuss and continue to talk through this. Matt, do you want to run through the general definition for me?
Yeah, I will. I'll jump in. So, pipe bursting defined. Pipe bursting is a trenchless replacement method, and with trenchless technologies, we talk a lot about, pipe rehabilitation, pipe replacement, and new pipe installation through trenchless methods. But one of the keys to keep in mind is that pipe bursting is a pipe replacement method. We're going to install a new pipe in the path of the existing pipe. And as part of that process, we're essentially trying to accomplish three things all at the same time. And we'll talk through how we accomplish that. But what we're going to do is we're going to fracture or split the existing pipe in its place. We're going to expand the existing soil that's going to allow or receive that new pipe to go in. And then that new pipe is actually going to be pulled in or progress through at the same time. So one of the real differentiating factors with pipe bursting is it's really the only method of pipe replacement where we can actually increase the pipe size or the pipe ID in place. Go ahead and skip to the next one, Alan. So there's really two primary methods that we really recognize inside of the industry today. And 20 years or so ago, when I first started getting involved with pipe bursting, there were probably a dozen or 15 different methods, and an old Army Corps manual outlined a lot of those. But the industry really talks about now the static or the pneumatic pipe bursting process. Pneumatic pipe bursting uses a soil displacement hammer and a constant tension winch that is affixed to the front of a new pipe, and as it is pulled through the ground, that soil displacement hammer is used to help fracture the pipe, expand the soil, and then the constant tension pull that pipe or progress it through the existing pipe. The static pipe bursting method, we're accomplishing the same thing. We're just accomplishing it a little bit differently. So instead of using that pneumatic hammer, we're going to affix a head to the front of the pipe, and we're just going to pull with a static force that is going to fracture that pipe and expand the soil. So I often explain the two, that you can put a nail in a piece of wood with a hammer and pound it in, and that's the pneumatic process. Or if you push hard enough, you can actually push that nail into the piece of wood, and that would be how I'd explain the static process.
So the actual concepts are exactly the same. It's just the mechanism as to which that force is delivered and the equipment that accomplishes that goal are what primarily changes through this. It is important to note that only high density polyethylene can be used for pneumatic pipe bursting itself. That's the only pipe that can be done through that. So
yeah, this is usually the point of the conversation where somebody asks, well, which one is better? And hopefully over the course of the next hour, you'll see that each one is used for different conditions. So the pneumatic pipe bursting process is typically going to look like this. One of the things to keep in mind, the pipe bursting method is less trench. It's not necessarily no trench. So there is going to be some excavation on a pipe bursting job site that typically consists of on the right of this photo, you'll see a pipe insertion. You may often see this called a launch pit or an insertion pit. At the other end of the photo on the left is where the winch or the receiving or the machine pit In small diameters, oftentimes below usually 12 inches, like in a sanitary sewer application, no excavation needs to be done on that left side of the photo. That can actually land or be received into a manhole. But this is what a typical pneumatic pipe bursting layout is going to look like. On the right, you'll see the new pipe. In this case, it's a continuously fused HDPE pipe that is laid out above the ground. The line that's going through that new HDPE pipe is the air hose that will power that pneumatic hammer. That pneumatic hammer, sometimes it will mount out in front of the head, sometimes it will mount back inside the head. And we'll show you a lot of pictures that show what that actually looks like out in the field. And then on the left side, you see the constant tension winch that's attached to the cable that's helped progressing that through.
So Edward Arrington asked a question here, Matt, about typical pit sizes for 12-inch, 15-inch, or 18-inch. That would also have dependency on depth. Service connections that are being performed in there, obviously, depth are there as well. As the presentation progresses forward, we're also going to show you pictures of what those actually would look like and how to estimate some pit sizes as we need it. Another thing in pneumatic pipe bursting that you can do, since you can use the actual manhole to daylight the bursting equipment, sometimes you can use a reversible tool to eliminate yet one more excavation for you. So.
Yep, and we'll show you some good pictures of those. But yeah, those are good questions. As we progress through, hopefully those we'll start to answer some of those questions. Go ahead and progress forward. So this would show you on the left is a small diameter reversible tool. If we were doing, say, an 8 or a 10-inch sanitary sewer, we'd use a tool like is on the left that would actually go up inside of the HDPE pipe. As it's received in the manhole at the other end, what we can do is simply cut the head off. And then the reversible is we just reverse the airflow back through the tool, which actually will cause it to back out of the new line that we just installed. So that tool doesn't have to come out of the manhole. For reference, that tool on the left is say it's an 8-inch tool and it's 7 or 7.5 feet long. That will go down inside of the new pipe and it will have a head on the front of it. The picture on the right, that was actually a job site I was on. That is a 14-inch pneumatic tool that is front mounted. In the case of this picture, we're replacing 15-inch RCP pipe. So in order to maximize the tool size, that 14-inch hammer mounts out in front of the head. And then that is, I believe it's a 16-inch ductile iron pipe size HDPE behind it. So that shows you kind of the scope and scale of a small what we'd call a small diameter head that's going to do 8 to say 12-inch, and then a mid-size head that's in that 15 to 18-inch range. The questions are coming in, which I like. So the photo on the left would show you a bigger pipe. That's a 16-inch pipe, and that has that same hammer that we looked at earlier, but it can be mounted up inside of the pipe. And then the picture to the right would be the head that would attach to that reversible tool. So when we land in the manhole, the only thing that's going to land in the manhole is that head you see in the right picture. The hammer is still up inside of there, but once we unhook the winch cable, we can just back the hammer out of our way and cut the head off.
Here's a video, if you guys can see the video. This is simply just a service connection pit that becomes eventually, and this is a pneumatic impact hammer pushing through this existing pipe. So there is some noise factor in pneumatic pipe bursting, and most of that noise actually comes out of the back of the pipeline as the air compressor that delivers that force through. That impact hammer just inches its way through it. In sensitive areas, you might want to give consideration to noise. Static pipe bursting doesn't make as much noise through that impact process. There still is noise associated with inserting the rods and pushing it through, but that video simply was there to illustrate that inching along of the impact hammer as it is continuous. Seem to have lost stuff here. Let's move to the next one. Here, if you want to talk about reversible pneumatic systems for a minute, Matt.
Yeah, so the video would show what that tool would look like going through an intermediate pit. An intermediate pit would be something like a service connection. One of the things with pipe bursting we do have to do is we have to excavate each one of the service connections. So that's what it would look like coming through the service connection. If you look at this photo, you got a whole bunch of kind of boxes that popped up here, Alan. If you look at this photo, that again in small diameters, 6, 8, 10, typically as high as large as 12-inch pipe, we can actually set the winch up into a receiving manhole, and then when we land that head in the manhole, we simply cut the head off and back the tool out. And in some applications, that will eliminate that downstream or receiving pit.
Oh, I seem to have some technical trouble. Maybe you could still continue to try to talk through it, Matt, if you can still see me.
Yep, I'm going to skip through a couple slides. So again, the next slide is just going to show that head being cut off and the tool being reversed out. Typically, this is the point of the presentation where people ask about lengths. How long can you do? What sizes can you do? We'll continue to kind of work our way up to that. But if I was going to say with a pneumatic process, pneumatic pipe bursting probably makes up 80 or 90% of the sanitary sewer replacement in the country. And part of the reason is really because of that ability to use a small diameter reversible tool and to land in a manhole. Typical lengths, they can be laid out by, depending on soil conditions, ground conditions, lateral counts, things like that. But typically an installation is going to be laid out based on physically how much or how large of a job site a crew can manage that day. So oftentimes it's manhole to manhole, or say 300 feet, or a crew can often do 2 manhole sections in a day. So that might consist of 2 insertion pits, 2 landing manholes, and then however many services that need to be tied back together that day.
I still seem to be having some trouble, so let me
see if
do it up here.
Alan, I can probably take over for you here.
Here you go. Let's see if you can get right in on static pipe bursting for me.
Yeah, it doesn't let me share my screen, Alan. I'm disabled here. If one of you can just give me control, I can share. This was usually the part in COVID when the kid would come running in and stick their head in, or the cat would run across the screen. Well, I can't share my screen with y'all, but I'm gonna keep going here. The other process is static pipe bursting. And again, static pipe bursting, we're accomplishing the same thing. We're just going to do it in a different way. So instead of using a air compressor with a pneumatic hammer, we're going to use a hydraulic pulling machine. And that hydraulic pulling machine, we're going to string what is typically a rod through the existing pipe. It can be a rod, a cable, or a chain, but in most cases, it's going to be a rod. So we will string a rod through the existing pipe with a hydraulic machine that's going to push that rod through. Those rods are configured a couple different ways. You may see a rod with an API style, or like a directional drill style thread that are 2 or 3 or 4 feet long. Or you may see a rod that has a type of a quick latching mechanism. Sometimes they're called ladder rods that can drop in, lock together. Those are pushed out through or paid out through the existing pipe. At the other end, the static pipe bursting tool, whether it's an expander head or some sort of a cutter. If we're in a cast iron or a water main, we may attach a cutter to it. Once that cutter in the HDP pipe is attached, then we'll simply reverse that hydraulic and we'll start pulling on those rods. Just for a kind of a scope of conversation, in say an 8-inch sewer main replacement that's 300 feet long, if that was being done pneumatic, it may be done with an 8-inch tool and a 10-ton winch. Where with a static process, that may be done with a 40 or 60 or 80-ton hydraulic pulling unit. So again, we're doing the same thing. We're just splitting the work up very differently.
So Matt, I was able to come back on,
right.
and it's made you the host. So if you'd like to share your screen from the slide where we're picking up, let's try that. Your internet service might be better than mine. So
yeah, it still won't let me, Alan. It just says host disabled participant screen sharing.
Try to.
So with static pipe bursting, the one thing that is a little bit different is we're essentially always going to excavate 2 pits. The hydraulic pulling machine is typically big enough where it's going to require a pit. There are and there have been some advancements in some small diameter and small tonnage systems that can actually fit inside of a manhole, but typically you're going to see an excavation done at one end that's going to insert the new pipe, and an excavation at the other end that is going to be the machine pit or the receiving pit. We got some great pictures we're going to show you here in a second.
Hopefully we'll get to it.
You don't have your boys screaming in the background, Alan. So that's
no, I don't. It's definitely a little different that way. So I'm going to try to log back out and log back in.
Okay. So those pictures will come up here in a second. Applications for pipe bursting, whether it is static and pneumatic, it is in the United States, gravity sewer replacement continues to make up the majority of pipes that are replaced by pipe bursting, and out of gravity sewer is typically because of the inventory. It's typically small diameter, so 8 to 12-inch pipe bursting probably makes up 80% of all the pipe bursting that's done in North America. But that's similar to CIPP or any other technology. Just because of the inventory of small diameter pipe is so high, that's what's going to make up the majority of the market. But there has been pipe bursting or gravity sewers done as big as 54 inches is the last number I've heard. The one thing about this industry is if there's a need, we'll find a way to do it. Oh, we are back. Look at that. Go ahead. Slide. So this slide is just showing what I talked through with the static pipe bursting machine on the right, and now the pipe insertion pit would be on the left. So this would be what a static hydraulic machine is going to look like down in the pit. One of the things to note is if you notice on the left side of the top photo, that's showing steel I-beams or big wooden blocks. As we exert that force to pull that pipe through, that force is exerted against the head wall or the face of that excavation. So oftentimes, the picture on the bottom left, you're going to see that trench box with those big steel beams, and that's how we're going to spread that force out across that trench.
That stops the actual tooling from advancing through the soil column. So that's very important, especially when we get into larger pipe bursting rigs and larger operations. Yeah,
the picture on the left is I think that's a picture from earlier. That's a 16-inch pipe being landed in a deep excavation in Boston. The picture on the right would show a smaller machine. That the picture on the right would be for a pipe size from maybe 6 to 12 inch, something like that. Go ahead to the next one. The next one is going to show what the rod configuration is. The picture on the left shows the quick lock or the ladder style rod. Other manufacturers make a similar rod that has a threaded end. The picture on the right is going to show what the hydraulic power pack is that's going to run that. That's typically a 50 or a 75 horsepower hydraulic power pack that it takes to run that unit. So on a static pipe bursting job, oftentimes the only noise at the site while the pipe is being installed is from that hydraulic machine running, versus with a pneumatic installation, you're going to have the air compressor running, plus you're going to hear that percussion from the hammer itself. Go ahead, next one. This picture is going to show a small diameter. Can you go one more? There you go. The picture on the left is going to show a small diameter. That's probably a 50 or 60 ton hydraulic unit in a shallow installation. And you can see here, they actually have to use the excavator to hold those beams up so they can shore that machine against the face. And you see the rods that are, this is during probably the rod payout process. So you see the rod that's going in the center of the machine, and that's going to get pushed out through the existing rod. On the left, that cage you see at the end of the installation, that cage is often put in, and that way the head can come in, land in that cage, the head can be cut off and removed, and then you basically end up with your new flush end of your.
It allows the crews to be able to remove all the tooling that's necessary, cutter attachments. So in static pipe bursting, you can put a whole series of different cutters, splitters, or other things in order to be able to remove it. We had a question just recently about any concern to use this method for deep burial, and we'll talk a little bit more about it as well. Yes, you can certainly pipe burst very, very deep installations themselves, and you need to take some consideration for the friction forces that are going to be created along that run from the weight of the soil column on it. But typically we just jack up the tonnage of the equipment as we go through that and make sure that those excavations are properly shored as it moves through. I did remove the videos, Matt.
Okay.
As much as I like videos, I think that's
Yep.
probably what was crashing this for me. So here's some of the applications. You can do it for gravity sewers, potable water, storm sewer, process pipe, and raw water. Again, gravity sewer and pneumatic pipe bursting make up the lion's share of the majority of pipe bursting operations. Static pipe bursting is the primary one that's used for potable water applications, as you don't have an air hose traipsed inside of that replacement pipe as we go through it. You can also use the pre-chlorinated pipe bursting application to make sure that that's sealed and disinfected on the inside. Fire water applications, Yulia, thank you again for the question. It's a similar process as we go through. If that fire water needs to be NSF or properly disinfected before putting it back into application, then you'd probably want to look to a pre-chlorinated pipe bursting or static pipe bursting rig itself. Existing pipes that can be burst, so we're looking at fracturable material. Those are going to be asbestos cement pipe, cast iron pipe, clay lined concrete pipe, PVC pipe, and a vitrified clay pipe. And the non-fracturable materials often have to be cut and scored as we go through those. There's a couple of stars on some of these, such as ductile iron and corrugated metal, that would be considered in the developmental process. Matt had talked about an IPBA classification that was adopted as part of the North American Society for Trenchless Technology. That will show you a table and will show you those detailed classification charts as we move forward as well. So existing pipes out there that are not candidates for pipe bursting are going to be those types of pipes that have some heavy reinforcement in the actual design of the pipe, such as a pre-stressed concrete cylinder pipe, reinforced concrete cylinder pipe, a bar wrapped concrete pipe. The actual design elements of how those pipes work together, that material works together to be able to create that pipe, are oftentimes going to be something that precludes us from pipe bursting those pipes. So we had a question here about bursting ductile iron pipes to install HDPE. What are the concerns about scarring it? There's a very big difference in the failure mechanism of cast iron versus ductile iron. So the failure mechanism of cast iron, when it gets to that top limit of its strength, it'll snap and brittle and break apart and then mix into the soil surrounding that replacement pipe. Ductile iron actually on its curve here will want to elongate as it finally reaches the end of its strength and then wants to reconform back on that existing shape that it had previously. So oftentimes the developmental contractor that wants to try to do this will score the bottom of the pipe and score the top of the pipe and use a larger expander to try to push it out, but it is still in the developmental phase and should be left to a contractor that has done that before and really is watching the risks for it. So here's some just graphic examples of it. Go ahead and elaborate, Matt, if you would, on CMP pipe bursting.
Yeah, and in the picture on the left actually shows a really good example of that. That was actually a job I did on the left. It shows, if you look to the left side of that pipe, you can see where that pipe is actually doing this before it cuts. Now that cutter that is being used is going to cut through that pipe, and then that expander behind it is going to open that pipe up. But you can start to see how it reacts. Where with a cast iron pipe, it's simply going to fracture apart. The picture on the right is corrugated metal pipe, and corrugated metal pipe. It just the technical contractor term we always come up with is accordion, where it just kind of wants to fall into itself. There have been contractors that have successfully done some corrugated metal pipe, but it is what the industry has called developmental. In some cases it can work, but typically what you're going to see is that head is just going to create basically a ball of pipe, and it's going to want to push a big ball of pipe out of the end.
Once you get it out the end, you'll have to cut it apart safely too. So that's an important part of it. Matt did touch about the range of diameters and lengths while I was having technical troubles through this. So there is no true technical limitation for the length of pipe bursting, but what controls that often is the design of the systems that we're replacing. So in gravity sewer, it's manhole to manhole spacing of that 300 feet that we look at. And then in potable water systems, it's going to be the valves, the appurtenances, the service connections, and productivity of the actual crew to do the work. So that's a very interesting difference between it. We were asked a quick question about pneumatic and static installation times. Once the actual pipe bursting process starts, sometimes those installation times are very, very similar. It's a lot of the prep work that takes more of the time itself. What big impact on it is just the length as to what you're doing. A depth and also soil conditions would make a big difference for you there. So great questions, and I love to see that they're keeping it come through here. And we'll move on to the very next one here.
Yep. Yeah. So comparing pipe bursting to open cut, and there's a significant reduction in carbon emission. I've seen, I think it was British Columbia chapter of NASDT 10 years ago, sort of created a carbon calculator to just see when you start really calculating how many dump trucks come in and out of an open cut site versus a pipe bursting site. It is a pretty dramatic reduction. If you look at the picture on the top, that is kind of any town USA with the beautiful trees down the edge of an urban street. That really is the character of that neighborhood. If you take the neighborhood in the picture at the top and remove those trees, the whole dynamic of that neighborhood changes. So it's being able to protect, not only trees, but it's landscaping and kind of the urban development. I actually did a job several years ago in Nantucket, and one of the things that I never knew until I got there was that when the Dutch elm disease came through a lot of areas, it wiped out these trees, and the trees in a neighborhood like that are a significant part of that neighborhood. So one of the other things, and especially in areas that have been developed, I see this a lot in the Northeast, especially, is the new line doesn't have to occupy a new space or create a new easement. There's a mentality for 40 or 50 years is you just abandon an old pipe in place and lay a new pipe next to it, and that works for a while until you start running into photos like the one on the bottom, and Boston, you just start running out of area to put new pipes. Significant reductions in traffic impact but that's typical with trenchless technology as a whole, is being able to get in, replace a pipe in 2 days instead of 6 or 8 days to open cut.
I consider the actual space of that existing pipeline to be the commodity when we get into the location of these bottom right pictures. It's just, you have a proven location as opposed to having to buy new right away or create space in a dense urban environment. That's really what we're looking at. So
yeah,
you're definitely right there, Matt.
yeah. And another one is the reduction in damage of existing utilities. We'll talk a little bit about some of the design around pipe bursting and pipe bursting around other utilities, but most open cut excavations, damage to utilities is done by the tooth of digging ditches.
So we're looking at pipe bursting versus other trenchless methods. So when we talk about cured and placed pipeline, that's actually a field fabricated pipe. So one of the big challenges now when we're looking at pressurized systems is it can be challenging to actually test the field fabricated pipe in a lab. One of the true benefits of high density polyethylene is how much testing it actually goes through at the factory level and how many ASTM standards there are that control manufacturing with this pipe. Pipe bursting is the only method where you can actually increase the actual ID of that existing pipeline, not just by cleaning the existing pipeline, but fracturing it out and then putting in a larger ID pipe through that. We do have hard surface connections. So if inflow and infiltration is a concern in gravity sewer systems, whatever you're connecting to in a CIPP method, that grout is not present. So it's actually a hard surface connection that can be done through. One of our compatriots does a good program or a good presentation, Mike Woodcock, on the actual return of investment through long-term planning on pipe bursting projects. And that full replacement factory manufactured pipe definitely can be a very advantageous for you when you are talking about trenchless replacement. So now we're going to look at some planning and design considerations. Really, in a feasibility analysis, what we want to collect for data, like you would do on any trenchless project, is really look at what the pipe material is, whether or not we're going to be able to access that pipe if we have a problem moment. Just because a portion of the pipe bursting pipe, the existing pipe, is encased in concrete does not mean that your project is over and dead in the water. Creative contractors can get around the utility conflict box like you see on the left here by abandoning that cast iron that was existing in place and simply using the allowable bend radius of the replacement pipe to go around it. We want to know some of these things, such as depth of that existing pipe, in order to be able to give information to the contractor of what they're really getting involved in. Are there any third-party utilities that are sensitive that can possibly be interrupted by this? They have limited outage periods potentially that we want to look at. The picture on the bottom right does happen to be what has previously been considered a showstopper. All that means is that pipe bursting equipment cannot push out the surrounding soil in the effect that we have concrete encasement. It just becomes another excavation. We already know that we're going to have excavation on this project. This is just another pit. Matt, I could be correct in saying that there's not a pipe bursting foreman on site that does not understand that he, at some point in time, could have an unplanned pit that he goes through. Is that right?
That is correct.
All right, so these are just feasibility analysis. If you're planning a pipe bursting project was underneath a railroad for its entirety, we probably would consider some other type of methods through that, but that's primarily because railroads are challenging to deal with. Matt, would you walk us through this chart, please?
Yep. So this chart was developed probably 10 or 12 years ago and was freshened up, I think 8 or 9 years ago. And the intent here was just to classify the degree of difficulty and the different considerations, the different factors that really can cause a installation to be more difficult or require some significantly additional planning and design. So the factors along the left, A, B, C, and D, really relate to the degree of difficulty. And the things that we're going to take into consideration are the depth of the pipe, the existing pipe ID, the new pipe diameter comparative to the existing pipe. So we use the term upsizing. We'll use a size on size installation. So that would be if we're going to put a new 8-inch HDP and pipe in the place of a 8-inch VCP pipe, for example, or a single upsize would be putting a new 10-inch pipe in the place of an 8-inch pipe. And then we can do double, triple, and larger upsizes than that. It takes significantly more consideration, but did a job a year or so ago that we put an 18-inch pipe in the place of a 10-inch pipe. And that was on that scale of a very comprehensive design, and a lot of things had to be considered, and a lot of these other factors could have caused that to be not practical. We consider burst length. Minimal is that 0 to 350 foot installation. Above that, we see installations on a regular basis that are 600, 700, 800 feet. We installed a line once that was like 1,300 feet, I think. All of these other factors were just right for that to happen, but we do always want to consider burst length. Another one to really keep into consideration is the original trench width. So every pipe we're replacing was dug in a trench. So sometimes you'll see trench widths that are very, very narrow, incompressible soils. I've actually run into trenches in the Northeast, and you see this a lot. Out west, you get in the desert where the trench will actually be laid in a small trench that was almost jackhammered to fit the pipe in, versus a relatively wide trench width compared to the new pipe. So if you're putting an 8-inch pipe in a trench that was dug with a bucket that this wide, that's not going to require a lot of additional planning. We also want to know about soil types, and what we really want to know about is soil types inside of that trench. So around that head, the one thing we talked about earlier is we want to expand the soil to allow that new pipe to go in. And one of two things has to happen is we either need to compress the soil, or we need to displace soil. So in that trench, we want to know the type of soils that are going to be in that trench. And then we want to know groundwater. So we take all of those different factors, and that's what's going to tell us if we have a Class A, a Class B, or Class C pipe burst.
So these classification charts here really show you what we consider to be some of the bread and butter. So this is the majority of pipe bursting that happens, which is a size on size, potentially a single upsize in the terms of Class B. These are the ones that happen commonplace every day all over the country, and most pipe bursting contractors are able to successfully do these installs. When we keep going to a Class C, we're looking at a double or triple upsize. So just be cognizant, depth helps displace or absorb some of that soil that's displaced. So the larger the soil column on top, the more room we have to absorb that displacement. It's not that you can't triple upsize something that doesn't have huge depth. You just have to understand and respect that you could be restoring the top above that pipeline itself as we go through it. So, and then we did talk about developmental, which we consider to be a Class D, which then we want to actually discuss those projects with the contractor, the technological limitations and everything else. So
one thing quickly, one of the things that really speaks to the maturity of pipe bursting is 20 years ago, it seemed like every job anybody was involved in were these developmental or very, very challenging. They were the jobs that just absolutely could not be dug. They were pushing the envelope. So a lot of 20 years ago, when we saw, what is somebody's experience with pipe bursting, it was these Class C pipe bursts. But now, as we've evolved and matured, most areas we go to, we see are used to the, like you said, the bread and butter, the stuff that's happening every day. Then you can have the discussions about pushing the envelope when it's time.
So these are just some general design elements that we're looking at when we start the design of a pipe bursting project. We're taking that preliminary planning and just fast forwarding it to try to continue to develop the bid documents surrounding a successful pipe as we go through that. They'd be similar to most design processes that you work for any pipeline project. We really want to make sure we've got that replacement pipe selected of what we really need, and we look for any sensitive elements that of the pipe bursting project that need to be continued through. So as I mentioned previously, we are using that proven conduit location. That is huge. And some designs that I've done, since that location is proven, I actually use ArcGIS to essentially design the whole plan set from, as opposed to detailed topographic survey. From a municipal engineer standpoint, it saves significant schedule time, and it actually saves pretty significant cost. But I also then understand from a contractual element that I require a bursting plan from the contractor in order to be able to prove that they understand what the job requires, and then continue to go from there. So there are some savings when you become more and more familiar with pipe bursting in order to be able to streamline your bid documents to make it quicker to go through. So we're looking at as-built documentation, GIS records, location of repairs, presence of third-party utilities, and especially sensitive utilities. We've had multiple questions about availability of the slides. We'd be more than happy to share them with you. Make sure you email dmueller@pepipe.org or me at aambler@pepipe.org, and we'd be happy to send those to you, as well as the engineer's package that is available as a reference. So Matt had talked a little bit about ground conditions, and really what we're looking and most interested in is the trench condition. And when we talk about soil borings for areas, to take a soil boring directly on top of the utility doesn't really work for us. So we really try to look for historical records to make sure that whatever they installed in the actual trench used good compacted backfill material. That's the best. Hard clays into cut rock trench is some of the worst for us. And then we look at that expander plus 4 inches or more. So we're looking at the expander head, not the existing pipeline as we move forward, and continue to go through that there. So we talk about soil displacement. This varies fairly significantly across the country with soil conditions. And it also varies based on depth and contractors' experience. So we've worked very closely to prepare some of this material with another contractor that hates talking about this word heave because he's never seen it. Although in Florida, sandy conditions where I've done a significant amount of pipe bursting in shallow depths, we see heave and it looks like tremors in some places. So of course that's an exaggeration, but here is a diagram exactly of how much soil is displaced as we go through this. And you can see that when we get into 4 sizes, upsize, we are pushing soil. If it's a deeper installation, that soil can sometimes push outwards and upwards and a little bit to the bottom. If it's shallower, we don't have the compressive forces of the soil column on top in order to be able to move through. We just got a question about analytical model for estimation of heave. There are calculations available to you. Please email aambler@pepipe.org and we'll send you in the right direction. A detailed analysis is available in the North American Society for Trenchless Technologies Pipe Bursting Good Practice Guidelines, 3rd edition from it there. So ground vibration is really analyzed for pneumatic pipe bursting. As we're moving that impact hammer across, it's sending a wave out into the soil condition. So scientist, Dr. Alan Atala with Bowling Green University, had studied the vibration limits. It's sending the peak particle velocity through the soil. And when we get into residential or sensitive structures, we're really looking at staying away from them some 8 feet through that. Buried structure, retaining walls, or other things that are fairly solid, we can be a little closer. One of the things about third-party utilities, especially fiber optic, which was a question that was answered earlier, if we know where those crossing locations are, a contractor oftentimes can remove the soil, so that way there's no conflict of soil displacement through that. So potholing those utilities are often very important to be able to do that there. So Matt, would you elaborate a little bit about project footprint?
Yeah, so with small diameter pipes and sizes, oftentimes the footprint can be very small. So the picture on the left is showing maybe a 6 or an 8-inch pipe replacement. So very small machine pit, a pit at the other end. You can see just kind of in the top right of the photo, there's a small excavation there. There's probably a service connection. This would be typical of like a Florida installation. I'm not used to seeing pipes 3 feet deep in Maine, but as the pipe diameter in depth, so does the footprint. So with HDPE pipe and even with the pipe bursting equipment, the deeper we go, typically those excavations are going to grow a little bit longer. And a lot of that is to get the radius to get the pipe down into the ground. But the picture on the right would show the installation of a 24-inch pipe compared to on the left of a small diameter pipe. So on the right, you see a 1,000 or a 1,200 CFM compressor. You see an excavator and a loader being used to handle the pipe. You see airlines being loaded out. So, you have to have the ability to access the pipe, and oftentimes the bend radius of that pipe, especially when you get a larger diameters, kind of impact how that site is going to lay out. But this kind of shows you the two scale of small diameter and large diameter.
As we get bigger, all the equipment that needs to handle it definitely gets bigger too. So those are site constraint limitations that we really need to be taking advantage of. High density polyethylene. Go ahead, Matt.
Yeah. So this would just kind of show you that same thing where you have a small diameter, maybe an 8-inch pipe on the right-hand side that is actually being kind of held in place by the front tire of that pickup truck versus a 12 to a 14-inch pipe on the left that is now being handled by a loader.
The allowable bending radius for HDPE is one of the most forgiving of all the pipe types. So it has the smallest allowable bending radius as far as what it can be pulled through. This pipe material type is some of the most durable and rugged. That is also extremely easy to work with in the field, which makes it very forgiving in a pipe bursting operation. So I'll talk a little bit about pre-chlorinated pipe bursting, which is primarily for static pipe bursting. So you would take a long run of pipe that you are going to pull into place, fuse it up. You do your pressure testing to make sure that everything, that the fusion works, everything's all set up that way. Then you can disinfect that pipeline, flush the disinfected water, and take 2 days of subsequent bacteriological samples to prove that the interior of that sealed pipeline is in fact disinfected. The day of the burst, you can decommission the main around 8 o'clock, 8:30 a.m. And then actually line this up and pull it into place. So the end of the pipe, after you've drained it, is often sealed to a swivel or an expander head that goes right on top of the high density polyethylene. Then you can pull it into place, make those service reconnections, and then flush that pipe out and plug it right back into service. So it is approved in many states throughout the United States as an easy way to take limited outage periods. So all this task can be accomplished from about 8:30 to 3:30 p.m. So in bedroom communities such as suburbs of Orlando, people would use the old main in the morning, and then when they come back after work in the evening, then they would drink out of the old main. Of course, COVID's changed a bit for activities as far as where people are working or how, but this is a very, very proven process in Florida and other places that we go through it. So again, there's lots of productivity tools available available for the high density polyethylene industry, that when we put one worker together to fuse everything, it may very well be a lonely job, but they are an integral part of that crew to go through that. We just had a question about excavating the services. Yes, they do need to be excavated because those are hard connections as we go through that. When we look at durability, long-term durability of the pipe, that is important to be able to make sure we have the hard connection either through mechanical service connections, electrofusion, or other mechanisms of fusion to be able to pull it through. So I'm going to skip through this one of shop drawing submittals, Matt, and then get right into a site layout plan if you want to talk about that for a second.
Yeah, so with a project that is going to be an 8-inch, small diameter sanitary sewer that's going to be put in, installed, and connected at the end of the day, typically the site or the layout plan is going to be relatively simple. It's going to, on a plan, it's going to show the location of the insertion pit. And to answer one of the questions earlier, we'll typically include the typical pit dimensions on that layout plan. It's also going to show the machine pit or the receiving pit location. One of the things that is important is to include that laydown yard location and footprint. So typically HDP pipe, for example, is going to come in either 40 or 50 foot lengths onto a job site. One of the pictures you saw earlier was we're using a rack system to load pipe to help manage it in the laydown yard. But that laydown yard is something that is on a pipe bursting job looks a little bit differently than it does on a typical construction site, where maybe one laydown yard serves the whole site, where oftentimes with a pipe bursting project, the project moves along so fast, the laydown yard kind of becomes a mobile site. And then the maintenance of traffic plan. So, are we going to do lane shifts, or are we going to actually have to close lanes? And then as part of that traffic plan, we also want to include how people are going to access their driveways, how business locations are going to access. As you get into those more complex jobs, we're going to include things pipe string locations. So like the pre-chlorinated pipe bursting process, for example, you may pre-fuse 5 or 6 or 10 pieces of pipe that are 3, 4, 5, 600 feet long, and stage those at the site so they can be pre-chlorinated, pulled in place. So where are those going to be stored? Or if we're fusing pipe for tomorrow's burst today, where is that pipe going to be left at the end of the day? Also, the bypass plan. Sometimes you see a bypass plan as complex as the pipe bursting plan.
So we'll look at site investigation again. So those activities that have been done during the preliminary and design elements, then of course now are under the ownership of the contractor. So sometimes a lot of the same work has been done again, but then the contractor is the one now responsible to make sure that they check off all of these items and make sure that there's nothing that would compare or stop the actual bursting operation as it moves forward. With a construction sequence for gravity sewer, we're looking at closed circuit television inspection. For gravity sewer, it's much more common to do CCTV inspection than it is for pressurized pipeline. It's just accessibility is a pretty big issue with the two, with decommissioning pressurized pipelines. Through that, pipe fusion happens in advance, as we saw. Manhole preparation. So then if repairs need to be made to the manhole to be able to strengthen it to withstand the forces from pneumatic pipe bursting operation, then you make sure to do that. Matt Timberlake is absolutely correct, especially on larger diameter projects. The temporary bypass system sometimes is significantly more complex than the actual bursting operation in and of itself. So, and then we get down to that pipe installation that becomes so quick in comparison to how many other things you're doing. So we look at significant less traffic impact, especially when we consider to a traditional open cut. The production limitations of an open cut job really allow only so much to be done via bell and spigot. And the simple gained time savings of a long run being fused in advance is where we're really taking advantage of schedule reductions that are fairly dramatic. In municipal environments, we don't often get to look at social, environmental, or the surrounding parts of economic costs, but the conscientious engineer would understand these and want to have their people or residents impacted less. You want to talk a little bit about manhole prep for?
Yep. So this would be for a gravity sewer application of what that, small diameter 8, 10, 12 inch sewers are going to look like. So the picture on the bottom left is going to show we often will call this a doghouse or a cutout. We're actually going to go in and we're going to remove some of the pipe wall that's going to allow that new that expander head and that new pipe to come in. So if we're replacing an 8-inch pipe with an 8-inch pipe, for example, the OD of that pipe bursting head is probably 10 to 11 inches. So we're actually going to knock out a hole around that so that pipe can come in. The picture in the middle is going to show the actual legs for the constant tension winch. And just in the top of that photo, you can kind of see the roller. That's where the cable would come down around and hook to the front of that head. The picture in the bottom right shows that pipe has come in and actually landed in the manhole. Now the winch cable would be disconnected. The hammer will be backed out the other end of the pipe, so 200, 300, 400 feet away, and then that head can actually be cut off behind that head, and you'll end up with a new pipe that can then be mortared and sealed back in.
We look at different things from maintenance of service, maintaining service as we go. So in potable water applications, we can often just drape a temporary PE pipe above ground, 2-inch, and then those service connections are connected to this while the pipe bursting operation is going through. In manhole or gravity sewer applications, we often just pump from one manhole upstream to one manhole downstream and take over a flexible pipe in order to be able to push through this. Protection of that temporary bypass is important as we advance through the pipe bursting operation. They can get pretty creative as to where they're putting these. In low flow conditions of storm sewers, you see on the right, you could take advantage of existing conduits in order to be able to put that temporary bypass. Again, for temporary bypass, high density polyethylene is one of the most widely used pipe materials for temporary bypass because it can withstand UV radiation, be reused repeatedly, and continuously butt fused and cut easily in the field that way itself. Matt, you want to look at setup of the pipe bursting equipment as well for static and alignment here?
Yep, so the picture on the left would be a typical pneumatic manhole exit scenario. So that shows the cable strung through the existing pipe, which is just down inside of those ladders. Now, it is important to get the alignment. We try to get that aligned so we're using the sidewall of the manhole, but we also need to take into consideration the condition of the manhole. Sometimes we get into a old brick manhole or a manhole that is significantly degraded where we may have to do work to that. Picture on the right is going to show a small diameter static burst. It is important to get those rods aligned. We want to have, because we're pulling, that pipe is going to go from point A to point B. So we want to get that pipe and those rods aligned so the center line is where we want it to be. And then with static installations, we have to do that soil, kind of the soil machine interface. And on this case, on the right, you see those 8 or 10-inch I-beams that are being used. Many times those are driven down into the ground just with the bucket of an excavator to shore up against. Sometimes you'll see a steel plate in there. But that's typically what the machine or the workhorse side of a pneumatic and static installation will look like.
So contractors maintain entire fields of different inventory of equipment that they have. So whatever that pipe burst is, sizes, material type, they vary significantly on how they actually accomplish this, especially when we get into more and more crews as we go through. Um, uh, Let's keep going here. What's next? So then we move that pipe from the laydown yard to the pipe bursting operation. You've seen some tricks of the trade with using tires or soft items in the field, truck tires, to rotate and align that pipe. We will talk a little bit about gouging. High density polyethylene allows a 10% gouge, and most of the scrapes that you get while pulling it over the surface of the road are well below that 10% gouge. We want to make sure when we are pulling it into place in the field that we do not pull it against something that has a protrusion or could gouge that pipe well beyond that. As a construction engineering inspector, once that pipe bursting operation is started, we can monitor its rate of advance, and we'll with the fused lengths of high density polyethylene, we simply count the length of the pipe between fusion joints, and as it advances through, see how long that took to be able to get your rate of advance as we come through there. So that's an indication if you're starting to slow down that there might be soil conditions that are tough. You might be dragging something along it, such as service connections that didn't fully shatter off or other things, and then we want to continue to monitor that rate of advance to ensure successful construction. So here's just some examples of what we're talking about in the field that are safe ways to be able to pull this pipe through. As a construction engineering inspector, one of the key things that is, once that pipe has arrived at the interface of the pipe bursting equipment and the existing pipeline, we're going to walk that pipeline to inspect it to make sure that we don't have any gouges or impending failure of that pipe as we move through it. What's interesting about high density polyethylene, its workability and durability, is that if you do have a gouge that you think is suspect, what I say is, when in doubt, cut it out. You simply use a dry chainsaw, remove that section of pipe, pull it together with construction machinery, butt fusion machinery, and you can often remove that cutout section within 15 to 30 minutes on site. So it's actually pretty forgiving pipe material in the field while they're working through and doing all this operation. So after that pipe installation, we look at mainline reconnections, post CCTV for quality control, then restoration, obviously, of the landscape, a surface restoration as we go through that, whatever needs to happen. We were asked a question about particle size for soils and rock underneath this. That is available information as a specification as part of the engineering package. So again, just email dmueller@pepipe.org or myself at ambler@pepipe.org. And within the excavation and backfill section, we'll certainly outline the allowable particle size. When looking at traditional open cut for installation polyethylene, it is considered to be a flexible pipeline, and so is PVC and ductile iron. So the same parameters that you would use to be able to install a safe trench are going to be the same parameters that we're looking at for polyethylene itself. Matt, you want to talk a little bit about reconnections for us?
Yeah, so mainline connections have come so far in the last 15 years, really so far in the last 10 years. The ability, the different type and style of fittings have really come a long way. So, whether it's temporary connections that are used, as part of the bypass plan, or whether it's the actual service reconnections, but we are going to excavate at each one of those connections. So the picture on the far right-hand side, that's a water main installation. Those pits were most likely laid out at the intersection of a T or a hydrant branch. So after the pipes are pulled in place, that new T or new hydrant branch can be put in place. The picture in the middle is going to show like a reconnection of a water service corp. This one, for example, is a electrofuge connection that can then be reconnected back to the house, and then basically a hot tap used to tap that back in. But you definitely have to plan for the location of laterals, any water service connections. The picture on the left would show a lateral pipe bursting pit. So, if you picture running down the street, you have the main, this is the lateral pit. Oftentimes what you'll see is you'll then see a lateral pipe bursting machine like the one in the far left can then be set up at that lateral, and you could actually then pipe burst the lateral back under. This would be a alongside service where you can then burst back over to where that pickup truck is. So now with you burst the main line, you burst the lateral back under those travel lanes, all through that small lateral pit.
So necessity is the mother of invention, and being involved in this industry for a while now, I've seen so much growth and development over the past 10, 15 years, as Matt really indicated here. So the available tools for you for even valve connections, AVK, one of the members of the Alliance for PE Pipe, actually has a ductile iron valve that has a polyethylene stub out that's forcibly pushed on a ductile iron or metallic piece with several lips that holds this polyethylene in place. And once you get that installed, you simply butt fuse to that side there as well. There are lots of different electrofusion fittings available to you to be able to expand this. And there's even nifty companies, one called Faction Fusion that does something called the low rider saddle, which when we pipe burst gravity sewer with a larger pipe, so here's the smaller pipe, and we put in a larger pipe, that theoretical spring line, which is the center of the pipe, raises just because of the size of the replacement pipe. The low rider saddle then comes at the bottom, so you don't have to change the elevation of the T coming to it as well. So just to clarify, we had a question about the gouge thickness as well. It's 10% of the wall thickness. So that changes with the pipe size and the DR. So once you get the actual wall thickness of that pipe, then that would be 10% of that itself. Lots of different ways to be able to do these, lots of proven connections. One of the key things that they try to do in the industry, both in pipe bursting and high density polyethylene, is to try to make things as foolproof as possible. The guys executing these projects aren't thinking about the ASTM standards. They're thinking about going home for the weekend or other things that they're doing. So we want to try to be as conservative as possible in the creation and manufacturing of these items in order to make it as foolproof as possible to install. Some other items that are available for you are in-trench butt fusion. So for larger pipe, you can actually lower that carriage down into the trench to be able to perform the butt fusions. The MJ adapter is one that's very interesting, very stout, robust connection. Essentially, you will put a flange beyond butt fusion, then they make this fitting for you. So it's very stout and robust when it connects to a valve. And then it can be done under wet conditions. So very, very robust fitting that way. We had a question earlier on, Matt, and I want to talk about it a little bit now, which is the largest size of pipe bursting that has been conducted to date. I was working a pipe rehabilitation project for very large cast iron and chased down this rabbit hole. The largest that I had been aware of by my discussion with lots of industry reps was about 48 inches to be able to be burst. But the equipment and tooling that is now being developed can get up to about 54 inches. Again, this is atypical. This is that very large pipe, very specific application. Most pipe bursting contractors out there would not own this type of equipment unless it was a very large job, but there are equipment manufacturers that would manufacture this equipment, have it available as a large rental fleet, which actually happens more often than not on specialty pipe bursting jobs. Do you want to elaborate a little bit more about large pipe, Matt?
Yeah, 54 is also the largest number I have heard. And again, I agree with everything you said there, Alan. Once you get into those large sizes, oftentimes there's only a few of the machines maybe in North America that can handle pipe that size. But like anything, if the demand is there, this industry will find a way to approach it. So it would not surprise me. But much like CIPP, things you heard of 15 years ago as the largest diameter CIPP installs, you now hear about happening every single day. So I think this industry will continue to do that. But the market is going to remain, we always say the bread and butter is still going to be that small diameter pipe.
So again, here's some more information on joint restraint. This happens every single day out in the field. Different mechanisms to do it. Evaluate your as a municipality. Evaluate your preferred reconnection method as we go through it. They also we get asked a lot about repair. They make lots of great fittings for repair as well. So there's lots of things and items out there for you. We talked a little bit about electrofusion, saddle fusion, socket fusion. These are all well-proven methods to be able to perform that service reconnection through them. They're very robust in the field, being able to deal with water through temporary bypass. There's lots of pigs and other things as well that the crews can use to be able to make sure that these are installed successfully. So we did talk about some construction observations. We were right at 12:15 Pacific time. I'm in Napa Valley as opposed to 3:15 Eastern Standard Time. So we'll keep going. And I think I primarily wanted to focus on scraping and gouging that is okay, and scraping and gouging that otherwise would not be okay. We talked about the wall thickness, 10% allowable. If you do not want the contractor to pull this above the road surface, which actually is a standard procedure, they can also pull that pipeline on rollers or other things in order to be able to get it to where it needs to go. Here you can see just some light scraping as we go through this. None of this really exceeds that 10% of wall thickness. The next one would be a prime example of something that was suspect. It's actually rather challenging as a construction observer to fully and very accurately, precisely expect or measure how this is actually, how deep of a gouge it is in the field. So then again, I look at that question of when in doubt, cut it out. And in this situation at 3:30 a.m. on the project on a Florida Department of Transportation road, the contractor simply stopped the advance of the process, cut out a 5-foot section, re-welded the pipe, and just kept going. So oftentimes we hear questions about scrapes and gouging, but it really is a pretty simple way to be able to get through this. We did talk about bedding and compaction on sensitive roads, DOT roads, where there's lots of heavy traffic. That density and compaction that you would receive for the backfilled and compacted excavation pits are important to be able to get and observe. So you do all the necessary testing as you go through this. Again, we have the resources available for you in the engineer's package to go through this. There is a data logger that is available that tracks whether or not those butt fused joints are done correctly. It simply adheres to the plugs right into the machinery that does this, and then it'll track your joint for you. This really is in sensitive installations for pipe bursting, where we want that extra quality assurance and control to be able to go through. Matt, I believe this picture on the right is yours. We only got about a minute left here before we release everybody. What is an unplanned pit, and what did you guys find?
The rock on the right was sitting directly on top of a 12-inch pipe that we were trying to pipe burst. And as I said, as that head goes through, the soil around it either has to compress or displace. And it was like trying to push that rock out through the earth, and that didn't happen. So that unfortunately was an unplanned pit. But that's what it looks like. It's you don't very often see that we call that select backfill in the Northeast.
And equipment failure can also be another reason as we do that too. So with that, I would like to stop sharing here and thank Matt for saving my butt during that technical failure. Sometimes we never know. This is as the Alliance for PE Pipes Roadshow program continues and expands. We are going to continue our webinar program, so you may very well see more of these from remote locations. Matt did notice there were no screaming kids. I miss them dearly, but it is nice to be in Napa sharing some wine with non-screaming kids. I don't give my wine to my kids anyway, but there you have it. Thank you, everybody. Keep an eye out for next month's program. And as the program continues to grow and develop, we've got some really good key webinars coming up. 3 parts for the American Society of Civil Engineers that'll close off a year's worth of webinars with them that cover all things high density polyethylene from A to Z. Matt and I are also very active in the North American Society for Trenchless Technologies, Pipe Bursting Good Practice Guidelines, and Pipe Bursting Center of Excellence program, which takes this concept and actually promulgates it out to 8 hours. So we wouldn't have a webinar without you. We've had well over 200 attendees make it this far with us. And then we also had over 400 register, which is fantastic to be able to say that as we go through it. So thank you so much for all your questions and your participation today. And we look forward to seeing you again in the future. Thanks, Matt.